So far we have looked at the various aspects of how a CPU works, right, or how the different components that are involved in the computation that goes on inside a computer work. Primarily, as we saw, there is an ALU, the arithmetic and logic unit. There are some registers that account for temporary storage of values so that you can perform the computations, and the reason why they are needed is because you have in general a memory that is used in order to store the data that you want to operate upon. And if that memory becomes too large, then it's not easy for that ALU to access all of it at one shot. So we break it up into a hierarchical structure, right? We basically go from the memory into the registers. From the registers, we perform the computations, and then we can go back to the memory. And incidentally, that memory could also perform input-output functions. In other words, it can be our interface to the outside world. Now, the question, of course, that arises after that is, what do we do with this, right? Because fine, we have the ability to perform certain kinds of computations. How do we put it to good use? How do we actually solve relevant problems? And the approach that is used for solving that or answering that question is what we refer to as programming, right? So programming essentially is the process of providing a sequence of instructions to the processor, the computer, so that it can solve a problem that we are interested in. So let's try and understand this by means of an example. And the example I'm going to take over here is something that is essentially some, we would have done in reasonably early in high school mathematics, right? It's the question of how do we solve a quadratic equation, right? And by quadratic equation, essentially what I mean over here is we have something of the form ax squared plus bx plus c is equal to 0, where x is an unknown, a variable, a, b and c are constants, right? And we want to find the values of x for which this equation holds true. Now from algebra, we know that there is a sort of standard way of solving this, right, and getting the solutions. And it's been known for hundreds of years. Essentially what it says is an equation of this form has two solutions, right? x1 and x2 is the names that I am giving to them over here. And in general, the solution is minus b plus or minus square root of b squared minus 4ac, the whole divided by 2 times a, right? And of course, what is interesting over here is a, b and c are all known values, right? In our context, we would call them constants, right, as opposed to x, which is a variable. And there are a few other values over here, the 2 and the 4, and also the pluses and minuses, square roots, a few operations that need to be performed, right? In other words, this looks like a perfect job for a computer, right? So let's see how we would go about solving this. So what are the steps that we need to take in order to get towards this computation, right? The first thing we would need to do is define where our inputs are, those values a, b and c, right? And what are the outputs, x1 and x2. Keep in mind that over here x is the variable, but for all practical purposes I'm not actually going to use the value of x anywhere, right? I'm not going to use the fact that it's a variable. I know a formula for the solution that I'm looking for, and I'm directly going to try and compute it. So in this context, a, b and c are the inputs to my problem, and what I compute with them, x1 and x2, are the outputs. Now what I'm going to do over here is I'm going to map these inputs into a memory model. And what I mean by that, the word memory model sort of sounds fancy, but what I just mean is I need to know where I can get them, right? So I'm going to assume that the value a is in some memory location that I'll call mem of 1, okay, and the value b is in some other memory location that I'll call mem of 2, the value c is in some other memory location that I call mem of 3, okay. It's just arbitrary. I could have chosen pretty much any way of storing them. It need not have been 1, 2, 3 like this. It could have been some other values. It need not have been in the same order. This is just one possible way of storing the values. All that I need is I need an address. If I want the value of a, how do I get it into my system, okay? Now further, x1 and x2 are unknown at this point. I'm going to compute them. So what I'm going to assume is that finally I'm going to put the value x1 over here in mem of 4 and the value x2 in mem of 5, okay. So these are all once again, it's an arbitrary mapping, it's a choice that I made. I can go ahead and put them out here. So this is what I mean when I use the phrase memory model, right? I have taken my inputs and figured out where to put them in memory so that they are accessible to my program, and I also know where I want my outputs to appear finally. Okay, now let's start breaking this computation down into steps that our computer can perform, right? So the steps will look something like this. I am going to basically compute the value b squared first, right? If I go back and look at this equation, I know that I have square root of b squared minus 4ac minus b plus square root of b squared minus 4ac. Now what that tells me when I look at this more carefully is, before I can perform this addition, I need to know what this value is under the square root. And in order to get the value which is under the square root sign, I need to first compute b squared, I need to compute 4ac, and I need to subtract the 2, right? That much seems clear. Now, should I compute b square before I compute 4 into a into c? That is not so obvious. And in particular, as we sort of go deeper into the theory of compilation and computer science, it becomes clear that actually there is no ordering here, right? These two, b squared and 4ac, are independent computations. If I had enough hardware, I could even have computed them in parallel with each other, right? But for the time being, I am going to assume that I need some ordering, right? So I will do b squared first. Now I want to compute 4 into a into c, but I don't have a hardware unit that can perform a multiplication of 3 numbers at once. So what I will do instead is I will first compute a into c, and then I will multiply that by 4. I could have done 4 into a and multiplied that by c, I could have multiplied 4 into c and multiplied that by a, many different ways of doing this. The point is, I have to pick one, okay. Now what you will notice is that on the left hand side of each of these equations, I have some new values, right? t1, t2, t3 and so on, right? Why are they there? Because I need placeholders. I need something that holds the temporary values that I am computing until I get my final result, okay. They are all temporary storage, and the word that we use to refer to them is that, once again, these are variables. Now these are variables in a different sense than the x was in ax square plus bx plus c equals 0, right? Over there, x was a variable in the context of algebra. We don't know what x is, we want to find out what the value, what it can be, right? So there are other terms that are used for that. In the context of computer programming, it's a very similar idea that we are using. We are computing something temporary, we want to give it a name, hence we call that a variable, right? The important thing to keep in mind is these things are temporary storage. We don't really need these results at the end. We only care about x1 and x2. So somehow I will perform these computations and finally I will discard these values t1, t2, t3 and so on. Now what I need to do is put these variables once again in appropriate places in the memory map. So for example, I can decide that mem6 is going to be t1, mem7 is going to be t2 and so on, right? I need to have enough memory in order to perform all these computations that I care about, right? But once again, where exactly I put them is my choice. So with all of this in place, right, let's go forward and actually work through the computation, right? So what I have over here, this on the left hand side is a model of my memory, right? Now one thing you will notice over here is I have started the memory from mem of 0. I had mentioned mem of 1 over here, right? But the common convention when we use programming, especially in a language like C, is that we start with the index 0, right? Now why exactly is that? That is related to how we sort of store a pointer to the beginning of a memory location, and then we sort of count offsets from that location, right? So the first offset, or the first value that we have is at offset 0, okay. It will become a bit more clear when we actually talk about arrays and slightly more complicated data collections in the context of a C programming. But for now, it doesn't really matter. All that I'm saying is, I'm starting from 0 and then going to 1, 2, 3 and so on. I could perfectly well have started from 1 and gone 2, 3, 4 and so on, right? Keep in mind that the only thing I care about as far as memory is concerned is, given an address, I should be able to get back data, and I should know where the address is corresponding to anything that I am interested in. As long as I have that mapping, I don't really care whether I start from 0, start from 1 or start from anything else, in fact. Okay, so now what am I going to do with this, right? The first thing is assume that the inputs are in the correct places. Over here I am assuming that A is in location 0, B is in location 1, C is in location 2. Alright. Now you will notice that I left locations 3 and 4 blank, right? As we previously discussed, I am finally going to put x1 and x2 out there, right? So let me start my computations, and what I am building up over here on the right hand side is the sequence of steps that is actually performing that computation, okay? So what's the first step that I want to perform? I'm going to write it this way: m of 5, right, which is basically this location out here, equals m of 1 into m of 1, right? It's a multiplication and both the inputs correspond to the same value. Is this possible? Yes, we can construct a piece of hardware which basically selects the same input as the same value from memory twice, okay, feeds it to both the inputs of a multiplier, and the result would be b squared. And what do I need to do? I need to put this value back into a memory location m5, right? So T1 goes in here. By the way, we'll talk about this again a little bit later, but you will notice that right now the way that I'm explaining this assumes that I'm directly manipulating memory, right? So m of 5 gets a value here and so on, right? Whereas we already had a discussion about why that's not a good idea, and I actually need to move data from memory into registers and then perform the computations and so on, right? Over here you can, for all practical purposes, just think of these m values as registers. So instead of m5 you could think of it as r5, the fifth register, if you wanted to, right? The important point over here is both of them perform the same function, storage, right? So I am able to perform all the computations that I need for solving a quadratic equation within this limited amount of storage that I have here, right? Which is why I am demonstrating the entire computation in this manner. Alright, so the first step has been taken, right? I have computed b squared and I have put it into m5. What would the next step be? Compute a into c, right? I call that t2 and I put it into m6. Okay. Next step, compute 4 into AC, right? Now further I am going to assume, right, all of these, there are some implicit assumptions that I make over here. 4 is a constant value, it's just a number, right? So I am going to assume that I can just directly say 4 times m6 over here, right, without having to first store 4 into a register. There are certain processors where this is not possible, right? I cannot have a constant as one of the operands for my multiplication, which is perfectly fine, right? If there is such a processor, I would need to break it into 2 steps. I would need to somehow get the value 4 into one of the registers and then perform the computation with that register and the m6, okay? But at least at a logical level, it seems clear why this is a simple enough operation that it could be handled with the model of hardware that we have looked at so far, right? The ALU plus some registers plus memory. So M7 now has the value 4AC, okay. Next step, M8, I have B squared, I have 4AC, let's go ahead and compute B square minus 4AC, okay. Move forward, M9 takes the square root, okay. So here I am assuming that I have some kind of hardware that's capable of performing a square root, right. If I did not, then I would need to figure out how to compute square roots using maybe some iterative procedure or some formula or something else, which actually would be a set of steps on its own. For now, I am assuming that my hardware is capable of performing a square root directly. Okay, so square root of b square minus 4ac is now sitting in T5, which is basically M9. Now I need to take a break and start computing something else, right, because there are other steps in the computation that I need to perform. M10 is going to get the value 2a, right. I am just computing this and keeping this here as preparation for a later step, right. If you think about it, what happens over here in step 6 is not going to be immediately used in step 7. Just like what was computed in step 5 is not being used immediately in step 6, but at some level I am going to combine them together later, right. So what is happening in step 6 is just one computation that's a preparation for a later step. We'll get to that as we move forward. Now the step 7 is going to be minus b. Okay. Now you might be wondering, hey, why am I even talking about minus b as a computation? There is no computation involved over here. The fact of the matter is, as far as the computer is concerned, yes, there is, right? Inverting a number, taking the negation of a number is actually a process, right, as far as a computer is concerned. For a human being, it's just trivial, right? I mean, we just think, okay, we have a minus sign in front of it, it becomes the negative of the number, right? Conceptually, we have a sufficient level of abstraction in our minds that minus b is just an intuitive and a trivial operation. But a computer actually takes a certain amount of time in order to compute the representation of minus b, right, the internal representation in terms of bits, which is why we have to make this an explicit operation. And as you can see over here, I put that down as one of my steps. Step 8 basically says, okay, very good, now I have minus b out here, I have square root of b square minus 4ac out here, compute minus b plus square root of b square minus 4ac, okay, just one of the values, okay. So M12, which stores the value T8, now has minus b plus square root of b square minus 4ac. Great. Now I am all set to compute x1, right? And remember, where does x1 go? It goes back into M3, right? So I don't need M13 out here. I don't need to go into a new memory location at this point. I just put it back into the M3 that was already sort of set apart for storing the value x1, right? And what does M3 at that point contain? It has minus b plus square root of b square minus 4ac divided by 2a, the solution that I wanted, okay. The next step would be also, I still need to do some more work, compute minus b minus square root of b square minus 4ac, right, put that also in one temporary variable. And the last step, minus b minus square root of b square minus 4ac divided by 2a goes into x2, that is memory location 4, okay. So this sequence of operations has actually finished my job, right? I have done everything that I wanted to do. I have performed the computation that I was looking for, right? There are a few observations that we can extract from here, right? Every step that I have written down in this sequence out here has been broken down in terms of something that I would call a computer primitive, okay. What do I mean by a computer primitive? It is typically, in this case at least, every one of these is an arithmetic operation. It's either a multiplication, a subtraction, addition, division, square root, or unit negation, right, unary negation, right. Those, in other words, are what I assume are available as primitives from my computer. Like I said, in case the computer that you are dealing with does not have a square root function, you have to figure out how to implement square root using the available primitives. In this case, I assume that square root is available, so yes, we can directly use it, right. If it's not, then in most cases it is possible to calculate the square root or approximate it in some way by using other operations. It will be probably a sequence of multiplications, divisions, and so on, okay. The next thing that you might, as I pointed out earlier, you hopefully see the thing clearly at this point, loads and stores were completely skipped, right. I assumed that A, B and C were already present in the right places, and everything else was just sort of performing a computation directly from these memory locations or these storage locations and putting the result back into some other storage location, right. Seemingly obvious steps, at least things that would be obvious to human beings, were completely spelled out in detail, right. So for example, the minus b, something that you would not really talk about as a separate step when you are describing it to a human, or maybe even something like 2a, right. It's okay, you need to take a and double it. Yes, there is a multiplication involved, but humans don't really think of that as a big deal. It's just multiplication by a constant, right. You think of 2a as a term on its own, but a computer needs to be told explicitly to compute that. The other thing that you might hopefully have noticed over here is we used a lot of temporary storage, right. All of these values out here are essentially temporary storage. How many of them were actually, how many distinct values out here were actually needed, right. For example, I computed AC, right? I put that into location number 6, and in the very next step I compute 4 times AC and put it into location number 7. I am never going to use AC by itself again, right? So could I have just overwritten this value out here, put 4 AC back into the same location? The answer of course is yes, right? I mean, what you imagine in an intuitive manner is perfectly correct. And as we will see when we go forward and actually start writing programs, it makes sense to reuse variables out here. Having said that, there is also another sort of approach to programming which is essentially called single assignment mode, right, where you would not do this. You would actually write out each and every computation as a separate assignment, as a separate location, right? And the reason for doing that is because that actually allows compilers to do a better analysis of where the data is being used and how to sort of optimize it in a more efficient manner, right? All those are considerably advanced topics which you will hit only when you start getting to how do compilers work. For the time being, you can ignore it. What is important to understand though is when you see something like this and you intuitively feel, hey, do I really need a new variable? I could have just used T2 itself to store 4 AC. You may be right? Of course, you need to check, you need to be sure that you are never going to use the raw value AC by itself again. If you are, then you will need to compute it once more, because the moment you overwrite it with 4 AC, that value AC is gone, right? But that's all there is to it. You can always overwrite values as long as they are within memory like this, right, and use them in whatever makes it most efficient, right, or easy to write your program. So in other words, the temporary storage could have been reduced for sure. How much could it have been reduced? That is actually a non-trivial problem, right? I mean, the actual analysis of what is the minimum number of storage locations required in order to solve a problem is itself an interesting computer science problem. It does have good solutions, right? And people know how to solve it. For the time being, you don't need to worry about it, right? You just sort of write your program without thinking too much about it. In general, you should be aware of what variables are being used, how often they are being used, and so on. But in most cases, compilers should be able to also take care of any redundancies that you have brought in by inadvertently. Okay, so the first example of a program that we considered was a quadratic equation solver, right? Now I'm going to take one more example which sort of conveys a different set of problems that you encounter when you get into the field of programming a processor, right? And the problem before us now is I want to find the sum of n values. Okay, it's not the sum of the first n numbers. What I'm saying is there are some n numbers. What are those n numbers? I'm going to assume that they are already stored somewhere in memory, right? Now there are a couple of interesting things out here, right? Like I said, I'm assuming that m of 0, m of 1 and so on are the values being used in order to store those n values, which means I'll go all the way from m of 0 up to m of n minus 1, right? Because I started from 0, I'll go up to n minus 1. There are n values out here. Each of these values, each of these memory locations holds a number, right? What I want to do is to add all of them together. So it should be clear to you that this is not something that I don't have a formula for this. I literally have to go through each one of them, pick up the numbers and add them. Okay, that's the first thing. The second is n could be large, right? Unlike in the previous case of the quadratic equation where everything including my temporary variables fit in less than in about 12 or 13 memory locations, right? Here n by itself could be 100, it could be 1000, it could be 1,000,000, right? And I don't know ahead of time how much it is, okay, which means that I might be using large parts of my memory that otherwise was not being exercised in the previous problem, right? So now our the structure of our CPU that we talked about earlier starts to become important, right? I'm going to assume that I have my ALU capable of performing the additions for me all inside the CPU, and that there is a block of registers out here that I will refer to as R0, R1 and so on, right? So M0 refers to the 0th location inside the main memory, right, the one where the numbers are stored. R0 is the 0th register, R1 is register number 1 and so on. These are inside the CPU and are purely temporary storage. Okay. With this structure in mind, let's see how do we go about writing the sequence of steps required to solve this problem. So now what I am going to do before I actually get into the details of the computation is that I am going to first start by setting up a counter. Okay. So R0, I'll arbitrarily pick one of my registers and say, hey, this is going to be my counter. Okay. Why do I need a counter? Because I need to go up to n, right? And I need at some point to be able to check, have I reached up to n or not? Okay. R0 is going to be used by me in order to keep track of that, right? There are certain kinds of processors where you might actually find that there are custom registers whose only job is to act as a loop counter. But we don't need that, right? Over here I can just use any one of my registers and make it behave like a counter. It's a temporary storage after all, just like any other computation that I wanted to perform. So I have set up the counter, and now what I do is R1 equals 0, and this is a temporary space for the sum that I am going to compute. Okay, the final value that I want to add up. Okay, now let's start performing the computations. R0 has now got the value 0, right? It started out with another way of looking at it is that R0 gives me the index in the main memory of the value that I want to pull out. Okay, so I am going to put in an instruction over here that looks like this, which basically says take the value corresponding to m of R0, right, and put it into the register R2, right. So in other words, load a value from the memory to the register. Which location of memory? That is pointed to by R of 0. So R of 0 starts off with 0, which means that I will take the value m of 0 and put it into R2, right. Now what do I do with this? Add it to R1, because after all R1 is where my overall sum is being computed, right. So now what does R1 contain? It contains the value 0 plus whatever is in R2, which is m of 0. Okay, so the first value over here, in other words, has been added into R1. Okay, so far so good. I've got to the point where I have added at least one of the values. Now what I need to do is increase R0 to the next value, right. So I go forward to 1, but now I need to check something. Is R0 still less than n, right? If R0 has become equal to n, see, after all I started from 0, okay, the first value to be loaded, and at the end of these computations I performed R0 equal to R0 plus 1. So now R0 has become equal to 1. Okay, if I wanted to add only one value, I am basically done at this point, right? I have got the first value R1. But if I wanted to add n values, in each time that I run through this, R0 is increasing, it's going 0, then 1, then 2, then 3 and so on. At some point it will reach n minus 1. In step 5, I will make it equal to n. And what I am saying is, if R0 is not less than n, then get out of this thing. But if it is less than n, go back to step 3. Okay, and this is the crucial part, right? Effectively what this is saying is it's a conditional branch. What's the condition? I check whether R0 is less than n, which means I have not finished adding all my n values, right? And if this condition is satisfied, that is R0 is less than n, what should I do? Go to step 3. What does this go to mean? You remember the program counter whose job was basically stepping across the instructions 1, 2, 3, 4, 5. I'll just take the value 3 and put it into the program counter. So the program counter will then fetch the next instruction from here. Okay. What will that do? That will basically pick up a new value of R2, right, from m of, now R0 is equal to 1, so it will pick up m of 1, put it into R2. What's next? I go forward to step 4. R1 will now get the value R1 plus the new R2 that I picked up, R0 will again get incremented to 2. I'll come here. Is R0 less than n? Let's say that n was equal to 10 or something like that. Yes, it is. Go back to step 3. What happens in step 3? I once again pull out R2 is equal to m of 2 now. Okay. R1, which already had the value m of 0 plus m of 1, will become m0 plus m1 plus m2. R0 will become 3. Is it less than 10? Yes. Go back, right? R2 will now get m of 3. R1 will become m0 plus m1 plus m2 plus m3 now, right? R0 will become 4, and so on until R0 eventually becomes equal to 10. At which point I'll have, if R0, which is 10, is less than 10, no, it's not. Okay, so I don't have to go back to step 3. What's the alternative? Just continue, go down to step 7, right? And in this case, what I'm saying is, in step 7, what I'm going to do is, whatever sum I computed up to this point, take it and put it into this memory location out here, right? The nth memory location, right? Is this necessary? No, it's just a choice that I made, right? I basically said I'll compute the sum of the first n values and put them into this memory location at the m of n, right? I could have chosen to do something else with it, right? Or I could have decided even just to leave it at r of 1, in which case, as of step 6, my program is already over. When I go to step 7, it should be something else, some other instruction telling me what to do, right? Because the computer, you could have an instruction out there that actually says halt or stop, or just shut down, okay? But that's usually not what you want. Usually there will be some other instruction there that says, okay, go to the next program or do something else, right? But this particular program, this sequence of instructions that we had, is done at this point. Step 7 is just, to illustrate how a store might work, right? I basically take an R1 and store the result back into a location in memory, right? And I say m of n gets the value from R1. That's interpreted as a store, okay? So this, in other words, is another program, right? Similar in terms of the kinds of operations. Again, you will notice that, everything here is a computer primitive, right? I assign 0 values, I load, I add. This is a somewhat complicated step, but it's still a computer primitive, right? I make a condition check, and based on the check, I branch, right? So both of these can be combined into one. There may be processors where you actually need to do this in 2 steps. I perform this R0 less than n as one computation, and then it sets some kind of a flag or a condition based on which I will then go to step 3, right? But logically, for our computer, I'm going to assume that this is one primitive step, okay? And that was all that was required, right? I needed to break my computation of adding n numbers into a set of primitives that the computer is capable of handling. So let's revisit this slide that we started with, right, which was, what were the steps toward computation? I assume that, I have my inputs, I know where my outputs are supposed to go, I have a memory model of where my inputs are, right, which is what tells me where to fetch these values from and where to put these results, right? And I break this computation into a sequence of steps, right? Put the variables into the appropriate parts of this memory map, and I need to put down a sequence of operations, right, that are needed in order to do the computation. This sequence of operations is what we call an algorithm, right? Strictly speaking, it is just a routine or a program, but normally when we talk about algorithms, this is what we have in mind. What we do, an algorithm is a sequence of steps, okay? And an algorithm needs to be codified in a way that a computer can understand. That is the sequence of operations that we deal with, okay? And this memory model that I deal with over here can be thought of as a data structure, right? In our cases, the quadratic equation had a very simple memory model, just constant data types that are stored in certain memory locations. The second one had a data structure, a very simple data structure called an array, right? and what we were doing was basically going through the different values in the array and adding them together, right? The point is that these terms, algorithms, data structures and so on, are useful from the point of view of helping us to sort of appreciate how to actually build programs in a systematic manner, right? So don't get sort of hassled by these terms. These are not something fancy. You don't need to be an expert in algorithms or data structures in order to, go through a course like this. The reason why these terms are important at this point is so that you are almost certain to sort of encounter these terms at some point as you go through, reference material for the course. And it should be clear that at the most basic level, an algorithm is just this, a sequence of steps, and a data structure is just an organization of data in memory, right? There is actually a very, a good book, a very well regarded book by Nicholas Wirth, who is one of the pioneers of computer science. For those of you who have heard of the language Pascal, he was one of the inventors of Pascal, pretty much the inventor of Pascal as far as I know, right? And he had this book, he has written this book way back in 1976, right, quite old, called Algorithms plus Data Structures equals Programs, right? And the reason for that title is actually, as you go deeper into programming, you will understand that a large part of understanding how to program is not so much about, just knowing the syntax of a language or knowing like what kind of, there are like clever ways of doing multiple things in a single step in a programming language. No, that's not how a program should be constructed. That's not the important part of it. The important part is the logical organization. What are the sequence of steps and how is your data stored? As long as you have clarity on those, you will have good programs, or you can at least, those are the first two steps that are required in order to build good programs. The rest of it largely comes from, practice at some level.